Type 0.1 plus 0.2 into almost any programming language, and modern silicon spits back an absurd mistake. Instead of clean math, you get a bizarre phantom fraction. This is not a sloppy bug in cheap hardware. Python, JavaScript, C, Java, and million-dollar supercomputers all stumble on this exact same elementary school calculation in identical fashion. A modern graphics card can simulate fluid dynamics and billions of light rays every second. Why does adding 10 cents and 20 cents completely defeat the most sophisticated chips on Earth? The reason begins with human biology. Because we evolved with 10 fingers. We organize our mathematics around base 10, where 1/10 is a neat, tidy single-digit fraction. Yet even our familiar decimal system cannot represent every division cleanly. Try dividing one whole by 3 and you get 0.3 repeating forever into infinite decimal space. Computers do not have 10 fingers. They only possess microscopic voltage switches. Inside silicon chips, every number must be expressed using only 2 physical states, on or off, 0 or 1. In binary, whole numbers are built out of ascending powers of 2. Moving left from the origin doubles each value, 1, 2, 4, 8, 16, cleanly building any integer you need. When you step right past the binary point, values do not divide into tenths. Instead, every column halves, 1/2, 1/4, 1/8, 1/16, and 1/32. Some fractions fit binary space perfectly. 1/2 is written as 0.1 and 3/4 is 0.11. These values are exact, finite, and completely error-free. Now try to construct 1/10. A half is too big, a quarter is too big, an eighth is too big, so you take a 16th, leaving a stubborn leftover fraction. When you perform binary division on 1/10, an endless recurring nightmare appears. The bits 0011 repeat infinitely, exactly like 1/3 in decimal, never terminating. A real physical processor does not have infinite space. It has a rigid memory register made of tiny silicon cells. At some point, the infinite repeating binary sequence gets brutally sliced off. When you take that chopped binary approximation and convert it back to decimal, the truth leaks out. You do not have 1/10. You have a tiny fraction slightly larger than 1/10. Why did you never notice this before? Because programming languages quietly lie to you, automatically rounding outputs when printing to keep you calm, hiding the mathematical chaos lurking beneath your code. To keep every computer chip from handling this rounding chaos differently, engineers gathered in 1985 to forge a universal standard known across the software world as IEEE 754. Floating point works like binary scientific notation. Instead of fixing the decimal dot in place, it breaks numbers into 3 components: a sign, a significant, and an adjustable floating exponent. In a standard 64-bit double precision float, you get 1 sign bit, 11 exponent bits for scale, and 52 fraction bits to capture raw numerical detail. Those 52 bits provide roughly 15 to 17 decimal digits of precision. Any digits beyond that boundary fall off the edge of the world, lost forever to silicon rounding limits. This creates a startling reality. Numbers on your computer are not a smooth, continuous line. They are discrete stepping stones with vast empty gaps where no computer number can exist. Even weirder, these stepping stones are not spaced evenly. Half of all representable floating point numbers sit between -2 and +2, spreading dramatically thinner as values grow huge. When you subtract 2 nearly equal large numbers, catastrophe strikes. The leading matching bits cancel out, shoving tiny rounding errors into the spotlight, magnifying noise into major mathematical errors. Now look at 0.1 plus 0.2 again. The hardware aligns their binary exponents, adds their mantisses, rounds to the nearest 52-bit slot, and creates that infamous trailing 4. In a weekend video game project, a tiny rounding error is just a harmless visual glitch. But in finance, aviation, and national defense, microsecond drift leads to catastrophic failure. In 1991, during the Gulf War, a Patriot missile battery tracked internal system time by continuously counting tenths of a second, multiplied by a truncated 24-bit float. The error per tick was microscopic, less than a millionth of a second. But after running continuously for 100 hours, those tiny errors compounded into a third of a second. For an incoming Scud missile traveling at Mach 5, A third of a second shifted the radar prediction box by more than half a kilometer. The system looked in the wrong sky. In financial markets, trading algorithms execute billions of transactions daily. Summing fractional cents with standard floats introduces phantom balance shifts that rapidly compound into millions of unaccounted dollars. In 1982, the Vancouver Stock Exchange created an index that truncated rounding down on every trade. Over 22 months, this silent rounding theft halved the entire index value. In 1996, Europe's Ariane 5 rocket disintegrated 37 seconds after launch. A 64-bit floating point velocity overflowed when crammed into a 16-bit integer slot. Even open-world video games suffer from this geometry trap. Walk millions of meters from origin, and sparse floating point resolution makes character physics jitter and terrain violently tear apart. If physical computer hardware cannot count to 1/10 natively, how do modern software engineers build reliable financial engines, scientific simulations, and bulletproof navigation systems? Solution 1 is decimal software types. Instead of binary hardware, languages like Python and Java store numbers as base 10 integer arrays in memory, trading execution speed for perfect precision. Solution 2 is pure integer arithmetic. Banking databases never store dollars as fractions. They store every account in whole cents or microcents, eliminating decimal points from hardware math entirely. Solution 3 is epsilon comparison. Never ask if two floats are strictly equal in code. Instead, check if the absolute distance between them is smaller than a microscopic tolerance threshold. Solution 4 is interval arithmetic. In safety-critical aerospace systems, algorithms track upper and lower bound intervals simultaneously, guaranteeing that true reality always remains safely trapped inside the calculation bounds. Why did engineers not just build decimal hardware from the start? Because binary circuits are exponentially simpler, vastly faster, and consume billions of times less electrical energy than base 10 chips. Your computer cannot count to 0.1, not because silicon is broken, but because it willingly sacrifices human decimal convenience to achieve unimaginable computational velocity. The next time your code produces 0.3 followed by that tiny 4, do not curse the compiler. You are witnessing the eternal fingerprint of binary infinity.